Hello and welcome to an honors physics math review video on units. Now, I love units. I think units are absolutely fascinating. The definitions of the different SI units, the SI base units, the whole metric system, I absolutely love it. So if you want to hear me really go on at length about units, get it at length because it's like something that you might measure with units. Anyway, talk to me in person if you want to hear a lot about units. As it is, I'm going to try to keep this video to just the stuff that you absolutely need to know for honors physics. Starting with the metric prefixes, I'm going to highly recommend that you memorize these prefixes: kilo, centi, milli, micro, and nano. Each one of these corresponds to an amount of units that prefix is worth, right? So we can add the prefix kilo to any unit, right? And that means it's worth 10 to the third or 1,000 units, right? So we can talk about kilometers, right? 1,000 meters, kilowatts, 1,000 watts, kilojoules, 1,000 joules, kilograms, 1,000 grams, etc., etc., for any metric unit, right? We can do the same thing for centi, 10 to the negative 2, milli, 10 to the negative 3, micro, 10 to the negative 6. That is the Greek letter mu, by the way. I know that looks like just a regular U, but it's not. And 10 to the negative 9th for a nano unit, right? So these conversions are fairly simple, right? Because we can just move the decimal point. So in this case, we are moving the decimal back 3, going from watts to kilowatts. 1, 2, 3 to get 5.6 kilowatts, because that is, right, 1,000, dividing by 1,000 there, right, to go from watts to kilowatts. And here, centi is 10 to the negative 2. We can move the decimal point 2 over this way and get 140 centimeters in 1.4 meters, right? So, moving right along here to scientific notation. So oftentimes, especially when we're dealing with things like nanometers, right, really small, we can write very large or very small numbers in scientific notation, and that is really just a convenience thing, right? Is numbers that are very large or very small have a lot of zeros or potentially a lot of leading zeros, right? And so by writing them as x times 10 to the n, where n is some positive or negative integer, right, then we can now keep track of how many zeros there are really easily, and that means we're not going to drop those zeros as we move that number along through our calculations, right? So scientific notation is really just like a time and effort saver. So, for example, we can convert 525 nanometers to meters. Well, nano is times 10 to the negative 9th, so it'd be 525 times 10 to the negative 9th, but you can't leave that as it stands in scientific notation because it has to be a decimal number, right? So this would be 5.25 times 10 to the negative 7th meters, right? Because it's always expressed like that with a decimal. And then megajoules. Mega is not one of the prefixes I need you to memorize, but it does mean 1 million or 10 to the 6th. So this would be 6.65 times 10 to the 6th joules, right? So again, what this number would look like is 0.00000525 meters, right? So to convert to scientific notation, we just move the decimal 1, 2, 3, 4, 5, 6, 7 until it's between the first two numbers, right? So then that's 5.25 times 10 to the negative 7th because I moved it over 7, right? What this number would look like is, right, or wait, I might have added one too many zeros there. 1, 2, 3, 4, 5, 6. No, that's right. So it looked like this, right? So you would go 1, 2, 3, 4, 5, 6, like that, and you get 6.65 times 10 to the 6th, right? So again, see how easy it is to drop a zero. I was even wondering, oh, did I put the right number of zeros? That's why scientific notation is useful. And remember, these two things, 5.25 times 10 to the negative 7th, 6.65 times 10 to the negative 6th, these are just numbers, right? They don't have any special, like, anything about them. They're just numbers, but expressed in a way that makes them easier to read. But you should treat them like any other number. Then we move on to dimensional analysis here. So dimensional analysis basically takes advantage of the idea that just like any number divided by itself is 1, or any variable divided by itself is 1, any unit divided by itself is also 1 and can therefore be canceled out. Right, so our goal is to cancel out our units until we get into the right one. So if we start with 70 miles per hour, we can write that as 70 miles divided by 1 hour, right? And so then we can first convert from miles into meters, right? So to do that, we know that there are 1.6 kilometers in 1 mile. And if you don't know that, you probably should, and now you do. And then we know that there are 1,000 meters in 1 kilometer. So you can cross those out. So now we're in meters per hour, because these are the units that remain uncrossed. We don't want to be in meters per hour. We want to be in meters per second. So now we need 1 hour on the top to cancel out this hour on the bottom. We know that there are 60 minutes in an hour and 60 seconds in 1 minute, right? So we've now crossed out our hours, we've crossed out our minutes, we are left with meters divided by seconds as the only units that remain uncanceled, right? And so we can take 70 times 1.6 times 1,000 divided by 60 and divided by 60 again. And I get that that comes out to 31.1 meters per second, right? So note that all of these conversion factors are things that are equivalent to each other on the top and bottom. 1.6 kilometers is equivalent to 1 mile. 1,000 meters is equivalent to 1 kilometer. So really all we're doing with this number is we're multiplying it by 1 a bunch of times, right? But we're multiplying it by 1 in such a way that it changes units every time so that we put it in the units that we want. And of course, mathematically, we're obviously not multiplying by 1, we're multiplying by whatever these numbers are, but like in terms of the concept, the reason this works is that we are really just multiplying by 1, just a weird form of the number 1. I don't know if that makes sense, but it doesn't have to as long as you know the process. Anyway, next up we're going to convert a density of 1.5 grams per milliliter to kilograms per cubic meter. So we start with 1.5 grams. Now 1 milliliter, you should know, is equivalent to 1 cubic centimeter. So we have 1.5 grams per cubic centimeter, right? And then we know that 1 kilogram is the equivalent of 1,000 grams, right? So we can cancel out our grams like that. And we know that 100 centimeters is equivalent to 1 meter. However, we're not converting between centimeters and meters. We are converting between cubic centimeters and cubic meters, so we have to take our conversion factor here and cube it, right? And so now we've canceled out our cubic centimeters and we're left in kilograms per cubic meter. So if I do that, don't need a calculator to do that, I should get 1,500, right? 100 cubed divided by 1,000. So 1,500 kilograms per cubic meter. So anytime that you are converting between square units, for example, square inches to square centimeters, you would need to square your conversion factor. Cubic centimeters to cubic meters, you will need to cube your conversion factor, etc. Lastly, another important skill that is related to dimensional analysis is just unit analysis, right? It's very important in physics to know what it is that you are solving for, what units in an equation are. So if you are given an unknown equation, you should be able to determine what the units of everything is in it, right? And then you see that unfamiliar equation and you can just quickly figure out what that equation is talking about. So for example, here's a bit of an odd equation. This is the equation for the velocity of a wave through a taut string. So velocity is in meters per second, and the Ft there is the tension force in newtons. Those are both common units, right? But then there's this weird thing mu, and like, oh, darn it, I wrote it down in my notes, but I forgot what the heck mu actually is, right? So, boy, I hope I can use this equation. Well, I can if I can just do some unit analysis. So let's find out what the units of mu are, and then maybe that'll tell us what mu actually is, too. So, all right, we have velocity in meters per second equals square root of Ft over mu. Now, something you need to remember, if you don't already have this memorized, you absolutely should, is that 1 Newton is equivalent to 1 kilogram meter per second squared. So, in other words, we have square root of kilograms times meters divided by whatever mu is. That's a terrible looking mu, but that's okay. Times square seconds. All right, so now what I can do is I can square this whole thing. So I get that meters squared per second squared is equal to kilogram meters divided by whatever mu is times second squared. We can multiply both sides by second squared to completely get rid of it, right? We can divide both sides by meters to do that. And so then we get that meters are equal to kilograms over mu. So mu should be equal to kilograms per meter. So mu is, in fact, what we would call linear density, the linear density of that taut string in kilograms per meter. So that is how you go about analyzing units. And again, absolutely critical to know that 1 Newton is equal to 1 kilogram meter per second squared. All right, so I hope you have enjoyed this video on unit analysis, and I will see you next time.